Welcome to the webinar, Don't Let Your Safe Operating Limits Leave You SOL Out of Luck. My name is Todd Stauffer. I am the Director of Alarm Management here at Exida. Thank you for joining. In terms of the audio for this webinar, everyone will be muted. If you have a comment or question, I encourage you to enter them into the questions box, and then we'll review them at the end of the webinar and see whether we can answer them at that point or as a follow-up email to everyone who attended. So with that, let's get started. I am the Director of Alarm Management here at Exida, as I said. I've been involved in creating alarm management tools and working with developing the standards that govern what happens with alarm management in the US and internationally. I helped edit and write the ISA 18.2 standard and many of the technical reports that came after it. And currently I have a role as a co-chair for a joint working group between the ISA 18.2 committee, which is the Alarm Management Committee within ISA, and the ISA 84/91 committee, which is the Functional Safety Committee. And what we are working on is a standard for process safety safeguards that do not go into a SIS, do not go into a safety instrumented system. And that was actually part of the genesis of the interest, or my interest, for this topic on safe operating limits. So it's kind of a collaboration between alarm management and functional safety. So a little bit about Exida, if you're new to the webinars. We were founded in 1999, so this is actually our 20th year anniversary that we are approaching and celebrating. The company was created to make the world, as in process plants, a safer place. So the initial focus was functional safety, and then we expanded that to include other kind of risk receptors, if you want to call it that, cybersecurity and alarm management. We do certification of people and devices. So if you have ever worked with a safety instrumented system and put together equipment that was SIL rated, SIL 2, SIL 3, chances are it was Exida that did that SIL certification. We also have a program for evaluating or training people on functional safety so they become competent and experts in the functional safety lifecycle, and a program for demonstrating that competence called the CFSE program. The last thing I wanted to mention is we have a suite of software for safety instrumented system design that covers the whole entire functional safety lifecycle and connects with alarm management. It includes a tool called SOL Alarm, which is for alarm rationalization and acts as a master alarm database. So why don't we get started with our topic for today, which is on safe operating limits. So we're going to talk about what they are, what are safe operating limits, why they're important, and then the bulk of the discussion will be on the results of a survey that we did several months ago that queried people around the world as to how they calculated and determined safe operating limits and how they used them. And what we'll hopefully be able to see is some of the differences in how people approach it, and areas where training and education about what safe operating limits are for can be improved, and perhaps also where industry can jump in and make things easier for folks that need to work with safe operating limits. And I'll start by saying this presentation that we're looking through today is an outgrowth of one that was delivered recently at the 15th Global Congress on Process Safety. This same topic, the original results and a paper, were presented by my colleague, Denise Chastain Knight. And one of the the things that we'll have a link to after the webinar is over is the actual paper that has the details of the research in it, so that you can download that and check that out if you're interested. So let's talk about what a safe operating limit is. So conceptually, before we look at the detailed technical definitions, safe operating limit is kind of like the speed limit for a process plant. You don't want to exceed it because bad things can happen. You can end up with an incident or an accident. So that's essentially what the meaning of the term safe operating limit is. Now, depending upon what region of the world you are from, you may not use this term in your day-to-day life. You may not be familiar with it. It's specifically applicable here in the US, and it comes into vogue from the OSHA Process Safety Management regulation. That was where the term safe operating limit was sort of coined, and the requirements to have them were documented. So even if you are in a location where you don't use the term safe operating limits, or you're not required to worry about them, there's probably an analogous concept that makes this information still useful. So let's look at some of the detailed technical definitions. One of the problems with application and usage of safe operating limits is that there is not really a well-established definition that's consistent and easily accessible. One of the more easy to follow definitions is on the CCPS AICHE glossary on their website, and you can see that here. And I just want to call out a couple of key elements of this definition, because what we're going to do is look at several of the definitions from different sources and kind of pull out the key parts to create our own working definition of what a safe operating limit is. So in this particular one, the key elements that we see are that safe operating limits relate to critical process parameters, so things like pressure, level, temperature, etc. And they are established or calculated based on a combination of design limits and the dynamics of the process. So key parts there. Another definition coming from CCPS guidelines for engineering design, which up until now is probably the most comprehensive treatment and discussion of safe operating limits. It has a very detailed definition that you can see here. Key elements that jump out here is, instead of focusing on limits, we're more focusing on an envelope that's defined by the limits, a safe operating envelope, with the idea that you should not intentionally operate the process beyond that safe operating envelope, or else you could end up with an incident or of a catastrophic failure or loss of containment. The other key part in this definition is that if you exceed the safe operating limit, then troubleshooting by the operator and other investigatory steps stop, and predetermined actions must be taken. So this could be manual actions by the operator, or it could be automatic actions by a safety instrumented system. And their purpose is to take the process back to a safe state or back within the normal operating limits. Another definition comes from a new technical report from ISA, Technical Report 84 4, Part 1. And this document actually does a pretty good job about expanding on what safe operating limits are, how they're calculated, how to think about them, and uses additional terminology that goes along with safe operating limits. But here you can see their definition is a little bit of a combination of some of the things that we looked at before. But one of the new things that they bring in is the idea that the set point for an independent protection layer, like SIS trip point, for example, could coincide with the safe operating limit in some cases. So it does provide some guidance for how to think about relief valve settings and SIS trip points, how they would line up in relation to safe operating limits in the overall operating envelope. Last thing that we'll look at is from the API. They have recommended practice 754, which is on process safety leading indicators. And they define, again, the safe operating envelope, where they more focus on the envelope as the part that's created from two operating limits. And they also emphasize the element that if you go beyond or go outside that operating envelope, that's when troubleshooting stops and predetermined actions must start or take over. And the whole idea is that this is preventing you from entering an unsafe condition or getting into an uncertain area. So that's the purpose of the safe operating limit. So if we consolidate those together to create a working definition or a working criteria, it would consist of the following points. So safe operating limits are for critical parameters. So not every parameter necessarily would have a safe operating limit defined on it. And the safe operating limit must be outside of the normal operating limits. It kind of makes sense. Also, in terms of establishing what the safe operating limit is, that would be done by a combination of looking at the equipment design limits, more on what that is later, and the process dynamics, so rate of change, things like that. It represents a safe operating envelope, and you should not knowingly operate the process outside of that safe operating envelope, or else if you do, then you get into a point where you must take action to take the process to a safe state. No more troubleshooting, no more optimization or control of the process. The idea is you've gone into an area where you should not be from an operational point of view, and you need to take the process to a safe state. So that's kind of the working definition that we'll use for this discussion as to what a safe operating limit is. So now let's talk about why they're important. So as part of the OSHA PSM regulation in the US, chemical companies, companies in the refining industry are required to calculate or determine what their safe operating limits are, as well as to document the corresponding consequences of deviation and corrective actions that operators should take. So for any PSM covered part of a plant, a process that's PSM covered, that information must be determined and documented and made aware for people to see and to people to know about, including it should be put into the operating procedures so that the operators are quite familiar with what those safe operating limits are. Another thing safe operating limits are used for is they're defined as a process safety leading indicator. They're actually a tier 3 leading indicator according to this triangle diagram that we'll talk about more later. But the idea is there are certain parameters that have been identified that one should track and watch, and you can use them to get a handle on where you are from a process safety management point of view and to drive performance improvement. So SOL exceedances are a specific recommended KPI, and they are a tier 3 KPI. The other thing that safe operating limits are used for is an evaluation of management of change, particularly related to process changes, and to make sure that a proposed change does not put the process outside of the safe operating limits, and if so, that would require some additional investigation, calculation, and documentation. So that's why safe operating limits are important, or one of the reasons they're important. Another reason they're important in the scheme of functional safety is if you look at this stack up of independent protection layers, we can see that toward the bottom here is an alarm and an operator response, and then above that is a safety system and the trip. Well, we could assume that your safe operating limits are somewhere in that region. They may be put in place with an alarm for the operator to respond to, or they may be such that if you go beyond the safe operating limit, then the SIS trips. So the takeaway is that they're one of the first layers of protection to activate. So in terms of monitoring them and watching them and knowing what they are and how to calculate them, it's very important because it's a good indicator of whether you are progressing up this envelope of increasingly worse hazards or increasingly worse situations. So it would help you to understand how often you're potentially having demands on your safety system or your relief valves. It also, as one of the first layers of defense, if it works well, can do a fantastic job of minimizing the demands on those other layers and preventing the escalation of a hazard to an incident. So it's really important to make sure that that particular independent protection layer is working. So in terms of this survey, over 150 people responded to it. Could be some of you that actually took part in it. It was quite a global cross-section. You can see from around the world. We had people chiming in with their information. And essentially what we're going to do now is go through the results, what we found, with the key questions that were asked, some of which are shown here. So things like what information is most important for the establishing of safe operating limits? Where do you store safe operating limit information? What do you do when you have an exceedance, etc.? So let's take a look at some of those questions. So the very first one had to do with operational limits as a broader category. And if you're familiar with defining safe operating limits, are there other operational limit categories that you also define as a company? And in this case, folks could enter more than one, or they could select more than one. And you can see just about as many people indicated that they define or use safe operating limits as they do process control limits. You can see others indicated quality control, and then there were some people that said they also actually define a whole separate category for environmental limits so that they can document emissions and effluent excursions. Now, when it comes to safe operating limits, one of the key questions of this entire survey is, what information do you use or should you use to calculate your safe operating limits? And this was a predefined list of choices. And if you remember the definition that we just talked about, where we made up a working definition, that should be brought into the thought process to understand the results here. So the choices were normal operating limits, safety instrumented system trip points and relief valve settings, normal operating limits, design constraints such as maximum allowable working pressure, mechanical integrity limits, integrity operating window limits. So based on the definition where we said safe operating limits would typically be set based on design limits and process dynamics, the expected answer was design constraints. And you can see that that was the number one answer, but not by much. In fact, about the same number of people said safe operating limits are set by SIS trip points. And that's really not correct. That's backwards. Now, that may be an artifice of how the question was asked, or depending upon the facility, if the design documentation truly wasn't available and what was established or what was documented and calculated were the SIS limits, then one could see why you might think that you're going to back calculate the safe operating limits from the SIS limits, but that's not really the way it would be done or should be done if you were doing it from scratch. Now, the categories for mechanical integrity or integrity operating windows, those are also things that we'll see should be included or thought about in the calculation of safe operating limits. So I expected some of those to be brought out as well. So you can see that over half the people essentially said the SIS trip points or the normal operating limit, and those really aren't the major things that drive creation of or documentation of the safe operating limits. So kind of indicates the need for increased training or understanding of what safe operating limits are for and how to calculate them. Now, as the follow-up question to that, there was a Freeform field for people to enter in more detail at a high level how they actually calculate the safe operating limits. And this is just some of the selected input to highlight some of the key areas or some of the key responses. SOLs are defined by design limits and design constraints, as we would kind of expect, by process technology. Mechanical integrity was highlighted. Process simulation and using safety factors against design limits. There were a couple of examples of that as the methodology for documenting. Some people called out the importance of the process dynamics and making sure there was sufficient time for the IPLs to respond. Another respondent mentioned risk-based inspection of equipment as it's installed and as it's working. And then finally, there was one that said, in a lot of cases, as I mentioned, the design information is not available. So it would be back calculated from the interlock settings or the relief valve settings, where you would assume that the appropriate calculations were done to establish them. And then by extension, you could come up with the safe operating limits. So the takeaway here is, though, that there's considerable variation in how people approach determining safe operating limits. So if you're going to use safe operating limits as a tier 3 leading indicator, the fact that everybody does it different is going to mean if you tried to compare results from one site to another, one company to another, you might not end up with the conclusions that you're hoping for, partly because safe operating limits mean different things to different companies. One of the other pieces of input that came in, I wanted to highlight because this is pretty solid information about how we would typically think about how safe operating limits line up in comparison to other types of operating limits. And what they responded with is you have, low and high settings for your operating range, and then next would come your alarm levels and then potentially interlock levels. And above interlock levels would come your safe operating limits, and then above safe operating limits would be your never exceed limits. And we'll talk more about what that term means a little bit later. But one of the points of confusion, one of the resources that exists actually showed the never exceed limits and the safe operating limits in a different order here. They actually had the safe operating limits being outside of the never exceed limits, which is part of what contributes to the confusion in how to establish safe operating limits and understand what they're really for and what you do with them. So then in terms of where do people document or keep their safe operating limit records, 30% of the respondents said they consider the operating procedures to be the master location for safe operating limits. So from a operational point of view and from an operator training point of view, that's probably the best place. Those are the people that need to know what the safe operating limits are and what to do. However, if you were thinking about a single repository of all your safe operating limit information, if it's sprinkled throughout your your operating procedures, and that's what you need to go look for, then it's going to be harder to track down and maintain management of change on your safe operating limits if they're scattered throughout all that documentation. So other respondents seem to take a different approach, and that was to have a single repository of safe operating limits. Now, there was great variety in terms of what system they actually use to store that information, from Documentum to SAP to SharePoint. You can see a lot of different data systems or other forms of documentation. One of the other questions then was, do you periodically review safe operating limits? 63%, almost 2/3, said no. 37% said no, we're not sure. So what's important is that although safe operating limits might appear as if they should be fixed throughout the life of a facility because they're based on design constraints, if processes and equipment changes and raw materials and flows and things like that change, then it is very likely that the safe operating limits may need to be recalculated or changed as well. So it does make sense. It is a good practice to periodically review your safe operating limits. Another question was whether process history, a data historian, is used to validate safe operating limits. And I'll talk about what validate means in a second. 55% of the respondents said yes, 45% no, or would want to be able to do that. So it was interesting that actually 24% of the people said they'd like to be able to use their process history to validate safe operating limits. So that seems like it identifies a need for industry. So potential area for tools to make that easy for people. So speaking of tools to do that, this is an example. It's a tool called C-Visual Explorer from Cayuga Partners. And essentially what this is showing is a snapshot in time where key process variables like temperature or reflux flow are shown on these parallel coordinates. And what the green lines represent, or could represent, is your normal operating envelope or your safe operating envelope. And each black dot is the actual current value at a certain point in time. So you could think of this as one time slice. Well, if you have months and months of data and you take all these time slices and put them on top of each other, then you end up with a profile that looks like this, again in C-Visual Explorer. So let's take a look at what this information could show us or what it could mean. It will calculate for that key process variable what were the min and max values over the time period, what is the normal operating envelope, either based on where the process is most of the time, or that could be parameters that are entered here. We know what we think the safe operating limit should be, and then we can see that there were instances, because there are lines here showing that there were times within the last year or 3 months where we did have exceedances of the safe operating limit. So you can actually see them with this tool. Not only can you see them, but it'll show you also, what else was going on at the time, and you can see how other key process variables, what was happening with them at the time that you had this SOL exceedance. So it can do a lot of useful information for you in terms of validating your safe operating limits. So it could actually calculate the percentage of time that you're outside of your normal operating envelope. It could calculate the percent of time that you're outside of your safe operating limits. If you change the safe operating limits, it can go back and kind of retrospectively calculate and tell you what percentage of time you would have been outside of your safe operating limits with a certain change. So there's a lot of great stuff that it can do for you. And as I mentioned, also, it really fleshes out the patterns showing the variables that relate to each other. So if you're trying to obviously minimize your safe operating limit exceedances, not only does it give you visibility to when they're happening, but also help you figure out what caused it and what other key process variables are involved in that event. So what do people do when a safe operating limit exceedance occurs? So most of the respondents said that they generate an alarm and there's action taken, whether it's manual action by an operator, documented in operating procedures, or if it's an automated response, it would be from a safety instrument system. A lot of people also referenced the fact that an incident investigation would likely be started or initiated. Some people called out that they would actually categorize this as a near miss event, and it would be recorded as such. And one of the related questions, 85% of the respondents said that one of the things that they would need to do if they had a safe operating limit exceedance was to notify management or report that to their management. So how frequently then do these safe operating limit exceedances occur? Without the actual data and the systems to do these calculations, this is kind of just an estimate at this point. So we can see that 61% of the respondents thought that it happened about once a year or less, and 32% thought it happened once a month or more frequently. So kind of quite across the board there. Now, one of the reasons why the occurrence or the frequency is important is because, as I mentioned earlier, exceedances of safe operating limits are treated or identified as a process safety leading indicator. Now, what's a leading indicator and why the heck are they used and where did it come from? Well, actually, as an outcome of the incident that occurred at the Texas City refinery, the Baker panel or Baker report had a recommendation to develop a consensus set of leading and lagging indicators for process safety performance in the chemical and refining industry. So the idea was to come up with a accepted or recommended set of metrics to look at, and the organizations that did that, CCPS, AICHE, IOGP, API, came up with a 4-tier approach where the tier 1 and tier 2 are actually loss of containment events. So those are the things that we really don't want to have happen. And that's why that part of the figure is smaller, because they're much more less likely to occur. And the area that you can actually maybe track more and see changes is in the tier 3 and tier 4 leading and lagging indicators. And in the tier 3 category, which is basically considered the challenges to your safety systems, that's where the safe operating limit exceedance resides. So the whole idea with leading and lagging indicators is to ideally define some metrics that one can follow, one can calculate, monitor, and that will directly help you prevent process safety incidents from occurring. And it's believed that monitoring of safe operating limits does have a direct correlation in preventing process safety accidents. Because if you're monitoring those and seeing that those events are going down, that also means that the number of challenges on your subsequent layers of protection, your safety instrumented systems or your pressure relief valves, are also being reduced as well. Now, the IOGP reference on process safety performance indicators, report 456, which just came out in November 2018, goes through and documents the different tiers of indicators. What are examples? What are considerations? What do you think about? And the example, or one of the examples that they fleshed out in detail for the tier 3 was the violation of a safe operating limit, in this case for a storage tank. But because it is quite amazing the number of tank overflow incidents that continue to occur, even with alarm management programs and process safety management programs. So safe operating limit excursions was one of the examples that were called out in that document. So then the question was, how many respondents actually use safe operating limit exceedances as process safety leading indicators? And the answer was about 63% said yes. Now, if all of the respondents worked in the US for a company or industry that was covered by OSHA, PSM, that answer should be 100%. But because this was a global survey and the need to document safe operating limits is primarily an OSHA-driven requirement, the usage of leading and lagging indicators is a industry global best practice. So this probably provides some indication of the adoption of this, but expecting 100% probably wasn't realistic given the demographics of the respondents. So this does perhaps give some indication that the knowledge and understanding of safe operating limits and what they're for and leading indicators probably could be improved. One of the other questions was asked about operators, and in particular, are they aware of safe operating limits and trained on them? 82% of the respondents said that they are, that yes. And ideally, that should really be 100%. Whether you use the term safe operating limit or not, whatever your analogous term or concept is, operators really do need to be trained on what the safe operating limits are for their associated operating areas. That should be part of their operating procedures. That should be reviewed on a regular basis as part of recertification of the operator or refresher training. So those are pretty important things. So for them to know the safe operating limits, what to do in the event that they exceed one, what's the consequences if they don't respond, all that kind of stuff should be well drilled for the operator. In addition, the information about safe operating limits and the visibility for the operator should be thought about in the alarm system and considered significantly in the alarm system in terms of presentation on the HMI screen, whether it's different from other alarms, perhaps the color and the priority and the horn tones that are used to announce that one of those alarm exists. It definitely makes sense to think about whether special treatment would be warranted for SOL limits being violated. So one of the other questions was, would it be beneficial to have safe operating limits available when you're conducting a PHA or a LOPA or an alarm rationalization? And 95% of the respondents said yes. So that is a potential learning or takeaway for tools that help document process hazard analysis and LOPA and alarm rationalization, that there should be a way to easily document safe operating limits and other operating envelope considerations and design constraints, and to be able to reference that appropriately as you're going through the task. Now, when it comes to alarm rationalization, certainly alarms that are there to prevent an SIS from tripping, a pre-trip alarm, or to prevent escalation outside of the safe operating limit, those alarms, information should be available about what the safe operating limit is, because the limits should be set in relation to the design constraints or other layers of protection. So would be very beneficial, very useful, very important to have information on your safe operating limits, ideally right in your master alarm database, so that you can factor that in when you're evaluating whether the alarm limit is set appropriately. And here you can see an example from our SOL alarm tool showing the ability to capture and see what the safe operating limits are when we are defining what the alarm limit is. So then, speaking of alarms, the next question was, do you define alarms in the control system to help you indicate an SOL exceedance? 69% of the people said yes, and this is really different from my personal experience, having done multiple alarm rationalizations and philosophy creations over the last 10 or 15 years. I don't see this talked about very often. So question is this data misinterpreted? And I think perhaps the question wasn't framed specifically enough. So it could have been interpreted as, do you get an alarm from the events that occur when a safe operating limit is exceeded, such as a relief valve lifting or an SIS tripping? And you may get alarms or notifications associated with them, but not necessarily related to the safe operating limit unto itself. And part of what this question was getting at was whether people use alarms to identify that a safe operating limit has been exceeded. Now, if it's an alarm that the operator needs to respond to, then for sure you have alarms to do that. But if it's for tracking purposes, that might still be a good idea to use the alarm system, because it's the best centralized data repository of the performance data. So one could define alarms to indicate safe operating limit exceedances and set the priority to a log or a journal, for example, where it's not presented to the operator. It just goes into the historical archive so that you could run reports and find out how often and when your safe operating limit exceedances occurred. So one of the potential takeaways is to use the alarm system in the DCS to be able to capture this information, paying special attention to whether the operator needs to respond or not, and that would govern as to whether the alarm was presented to the operator or just sent right to the journal. Now, one of the other pieces of information that was gained as part of the study was there are many people that record SOL exceedances or need to document them use a different system other than their control system, HMI, to do that. And it would make sense to me that it would probably be best if it was in the DCS rather than a totally separate system that's one or two layers removed from the real data and the real action. So in terms of the recording of safe operating limit exceedances, 52% of the respondents said yes, 48% said either no, that they don't, or they don't, but they would plan to in the future. So again, this might be an area where tools could help make this process easier for people, and there appears to be a desire to do that. The API standard talks about some of the other information that should be documented along with the exceedance, stuff like what was the peak value, how long was it in exceedance, and ideally to determine and document what the initiating cause was. Now, one of the paths to increased standardization and adoption is a better definition for safe operating limits. It's also definition and consistent use of other terminology related to safe operating limits. And we've talked about two different terms, one being design limit and another being never exceed limit. Now, the design limit is defined actually in the new ISA technical report number 4, has some good definition and guidelines for design limit, never exceed limit, and shows it pictorially in relation to the safe operating limit. So I think for the first time, you have a figure that shows you where the normal operating limit is, where your safe operating limit is, how that compares to your never exceed limit, your design limit, and then where would you expect your IPLs, your independent protection layers, to be staged. Typically, their set points would be between the safe operating limit and the never exceed limit. The next couple slides provide additional detail on the definition for design limits and not to exceed or never exceed limits. Design limits here, you can see it talks about mechanical integrity, and it talks about use of design specification values like maximum allowable working pressure, which is a common thing that people use to help establish safe operating limits. When it comes to the never exceed limits, this is a pretty interesting and important concept. It talks about the factors that are used to define the never exceed limit, and they are the design limit to start off with, but it also talks about age of the equipment and the operating environment and the maintenance and the integrity. So the lifespan of the equipment and the condition of the equipment actually would impact what the never exceed limit is. So the design limit may not change over time, but the never exceed limit might, to indicate or to show that the integrity of the equipment has changed based on the fact that it's been in service for 20 years or whatever. So additional information to help understand how safe operating limits are calculated and how they compare to other known values. Now, there was a paper presented at last year's Global Congress on Process Safety that talked about safe operating limits and how do you define them and what do you do with them, similar to what we just talked about. That was done by a gentleman from Celanese, and these are some of the key takeaways that they had in terms of the characteristics for what defines good safe operating limits. I just want to go through them quickly as part of this presentation. So safe operating limits, if they're defined well, would be indicative or predictive of Tier 1 process safety incidents. So the idea of having a good Tier 3 leading indicator and monitoring it and showing progress and eliminating that, if it's a good leading indicator, you should be effectively reducing the likelihood of a Tier 1 event. They also thought that the number of operating limits, safe operating limits that you have defined for a unit should be relatively few, enough that an operator could actually commit to memory and remember and memorize. They also pointed out the use of design limits when it comes to establishing the safe operating limits. A key point that they made as well is that your instrumentation, the range of your instrumentation, should be wide enough to be able to capture the process going up to your safe operating limits and potentially exceeding them. That should not go beyond your instrument range. And they also talked about the importance of configuring and documenting alarms with operator actions based on the rate of change of the process to make sure that the operator had sufficient amount of time to respond to the alarm to prevent escalation of the incident. So kind of drawing to a close and a summary of what we've been talking about and some conclusions. So we talked about some of the different ways that safe operating limits are calculated, the different thought processes, the different parameters or things that are used to calculate that. And of course, if there's differences in that, that means any assessment of how effective the tier 3 leading indicators are for safe operating limits needs to take that into account, the fact that safe operating limits may be different from one site or one facility or one company to another. So that impacts how you can compare your leading indicators from one site to another. So the highlights the need to come up with more of a standard definition and more accepted and consistent terminology, such as design limits and never exceed limits. Another thing that we take away is that in addition to the design limits and constraints such as maximum allowable working pressure, that we should also consider the mechanical integrity limits and integrity operating windows as part of the establishment of safe operating limits, and also the importance of the rate of change of the process in establishing effective safe operating limits and ensuring that appropriate action can be taken. In terms of some of the lessons learned from what we saw, we highlighted some areas where additional training or education would be helpful, not only in the determination of safe operating limits, but the usage of leading indicators, certainly the significance to operators of what the safe operating limits are for and what they mean. We also highlighted a couple of scenarios where safety lifecycle tools could perhaps better support what the safety practitioner needs to do with the safe operating limit information. And we also talked about connecting safe operating limits and alarm management in terms of making sure that safe operating limits are referenced or known during the rationalization process, and if prioritized accordingly based on the operator's response, potentially using the alarm system as a means of capturing safe operating limit exceedances, as well as ensuring that the process dynamics are set up to give the operator adequate time to respond. So at this point, I'll say thank you for attending, and let's take a look and see what kind of questions we have and whether there's some simple ones that we can address here directly, or whether they might all best be served by being addressed offline here. And I think these would most likely be best addressed offline. So I will create some hopefully thoughtfully crafted answers to the questions that you all have proposed here. And that'll be included in the email follow-up that provides a link to this recorded webinar and to the slides. So on that note, I'll say thank you again for attending. If you're interested in learning more about alarm management, we have a series of pre-recorded webinars on the Exida website that I would encourage you to attend. We also have a new online alarm management training class that includes a exam to be certified as a alarm management practitioner. So thank you for attending, and I hope you choose to continue to listen to Exida webinars. Thank you and have a good day.